Welcome to today's webinar on why do you need error correcting code ECC memories in your system. I am Brian Heineman, Principal Apps Engineer with our TTS group here at MAXIM. And joining us today is Carlos Rodriguez. Carlos is a business manager in the low power microcontrollers group at MAXIM Integrated. He obtained a double master's, MBA, and MS in electrical engineering at the University of Texas at Dallas in 2017. So with that introduction, take it away, Carlos.
Thank you, Brian. I appreciate it. So first of all, thanks everybody for joining today. Appreciate you guys joining us and learning more about MAXIM. So today, like Brian said, we're going to be talking about error correcting code memories. And hopefully by the end of this presentation, you guys are going to know what exactly ECC is if you don't know that already. But also if it's really a valuable feature that you guys can add into your current designs. So let's go ahead and get started here. So the first thing I want to do is actually kind of talk about the two types of errors that we typically see within our integrated circuits. So the first one is going to be, we're going to start with hard errors here. These are essentially errors caused by bad semiconductor manufacturing, whether this bad wire bonding during, BGA packages or TQFN packages, maybe burnt transistors that happen while testing the parts, or potentially actual like errors that happen during the lithography process, whether your mask was put in the wrong location, or maybe there's a particle within your mask that whenever you expose the semiconductor, you get some issues there. Some of the things that are unique to this type of errors is that, one, they're going to be repeatable errors. In other words, if you run the same test over and over, you're going to be able to catch that error, and it's going to be localized within a certain area of the IC, right? Because this is actually a physical error, which means it's maybe like some flip-flop or some transistor that is malfunctioning. So that's hard errors. Now moving on to the soft errors here, this is a little different, and maybe you guys are not familiar, so I'm going to give a little bit of background on what soft errors are. And I might get a little scientific here, but I think it's going to help understand the background of why this type of errors happen. So these soft errors are actually caused by external disturbances, which actually alter the functionality of our transistors or our flip-flops or our integrated circuit in general. This could be either fluctuations in signal voltage, maybe like a noisy power supply, and inductive coupling effects. But more importantly, the great majority of this type of errors actually happen because of high energy particles hitting our product silicon. And let me just kind of explain this, because I know this sounds a little weird here, but let me explain what happens. So essentially, there's actually cosmic rays coming from the sun and actually galaxies raining down from the sky, which actually contain high energy particles. And there's actually two different paths. You can either have high energy particles hitting the silicon directly, coming directly from the cosmic rays. Or two, they can actually create a domino effect. These energy particles hit and create some of the oxygen and nitrogen atoms that we have in our atmosphere. And they create a domino effect where it actually, after a nuclear reaction happens with those atoms, it shoots out new neutrons that then those hit our silicon. Now, what I mean by domino effect is that there's actually a second nuclear reaction happening within our silicon, which creates our silicon atoms to shoot out different particles within our silicon. And if it hits the right locations within our integrated circuits, it can actually change and create bit flips within our memories. In other words, if a transistor actually starts, it gets flipped and it starts allowing current to move through, then within a flip-flop, then you're going to have, maybe if you were storing a 0, now you're going to start storing a 1. or the other way. Maybe you were storing a 1 and now you're going to be storing a 0. What's interesting about these errors is that they actually not only happen from cosmic rays, but they could actually also happen from packaging and bond materials actually emitting these particles and creating the same effect. Now, instead of coming from the atmosphere, from space, they're actually coming within the same package. But same scenario, you know, whether it's coming from cosmic rays or it's coming from the emissions of the package itself, the effect is going to be the same. At the end of the day, these things are creating bit flips within our memories. What's unique about these errors compared to the hard errors is that they're not repeatable, because we don't really know when a random alpha particle or a neutron is going to be hitting our silicon. This is something that we cannot control, and they're not necessarily repeatable. Okay, so with that, now you understand both what hard errors are and soft errors are. Today we're going to be talking about more soft errors, and we're going to be talking about why this is an issue now versus before. You know, why do we care about them now, and why didn't we care about them before? So initially, when we started creating semiconductors, we actually started with, you know, micrometer technology. This was actually relatively big transistors within our ICs. This was, you know, 40, 50 years ago when we started the lithography process, and we started discovering this new method of manufacturing semiconductors. And over time, because of Moore's law and just the need to have smaller and smaller devices, we became really small. You know, we went down to what we have right now, down to 40, 30, 20 nanometer technology. And while this is awesome because now we can get smaller products, you know, smaller wearables and smaller computers, you know, thinner computers, all our products are really becoming a lot more, a lot smaller and a lot easier to transport from one place to the other. But the problem with this is that it has caused transistors to become a lot more susceptible to disturbances like the alpha particles that we just talked about earlier. Whereas before, you know, we used to have these big transistors, which these flip-flops that had really large charges. Now these alpha particles hit our silicon, and those small charges from the nuclear reactions that happen, that can actually make the transistor to behave in a different way that you were expecting it to. So that's definitely a big trend. I think this is actually the bigger trend. You know, this is going into smaller technology is really causing for us to be more careful about our functionality of our devices. Now, the second thing that actually happens too over time, that has happened over time, is that now we really require high levels of reliability within some of our applications where we are including electronics. So whether it's in the IoT space, in the medical space, in the financial space, there's a lot of reliability issues that you want your device to perform at the highest level possible. And I'll actually be talking about a few examples in the next few slides. So those are the main two things here, and that's why it's affecting us now. Now from looking at a higher level and what it's actually doing, like what are these bit flips really doing to our devices? Let's think about your laptop. You know, we have your memory corruption within your laptop. You know, Excel files not working all of a sudden. You know, you haven't used them for, let's say, a year, and all of a sudden you try to open them and they're not working. This could potentially be an issue with bit flips happening because of this phenomena. Also, maybe programs not running correctly, you know, loss of wire and wireless communications, or even the very well-known blue screen of death, right? Where all of a sudden you try to turn on your computer and you have a blue screen, the Windows blue screen that doesn't really let you do anything with the computer. These are actually issues that could potentially, I'm not saying all of them are caused by this type of bit flips from this phenomena, but it could very much be the reason why we're seeing this type of errors. And this actually, I would say this happens pretty often. At least to me, this happens at least once or twice a month. You know, it's a pretty often and repeatable thing that happens. So now there's different things we can do to improve this and to, make things a little bit more reliable. One of them is improve manufacturing techniques. But I mean, this is something that is not dependent on us, on the user of the integrated circuits. It's based on, we have to depend on third party to do this. So this is not super practical. The second thing that you could do is maybe reset your system so that you were able to recover the memories and it goes back to the memory that you were expecting, especially in SRAM memories. But sometimes you actually don't even have the luxury to do this, right? So there's a lot of applications where you don't really have the luxury of resetting that system to recover the memories, and that's where error correcting code comes in. Error correcting code is actually, just as a really brief description, error correcting code is actually used to be able to detect bit errors. And but more importantly, it's able to correct those errors on the fly without you having to turn off your system as the program is running. If ECC is enabled within your memories, it's going to catch those errors and correct them. And the functionality of your software or your program is going to continue as normal, and it's going to be seamless for the user. ECC is actually really old. This is actually an old technology. From the 1960s, 1970s. But it's actually now becoming important more in microcontrollers. This is actually, ECC has been applied into other types of integrated circuits, but it's now becoming more important into microcontrollers because of the reasons that we mentioned before. It really helps you increase the robustness of the entire device and the memories, and it also allows you to decrease the type of system failures that we would expect from bit flips happening within our system or within our IC. And, MAXIM, we believe that it's so important and it's becoming such a bigger trend that we're actually standardizing this feature in essentially all our microcontrollers. It's becoming essentially a standard feature across the line. So let's now that you kind of know what ECC does and you might be wondering, do I really need it? I think my system is already super reliable. Do I really need to add ECC to the application? And the answer to that is it depends. It just kind of depends on the type of applications that you're trying to go into. Most of the times, we're able to accept the frequency of errors. And like I said, maybe you have the luxury of resetting the system and then you're back and running and, it doesn't really affect the user. However, there's 4 different examples that I'm going to be talking about here in this slide that's not the case. One of them is maybe difficult of accessibility. What I mean by that, it's like physically accessible. The device itself is not physically accessible. Maybe in an agriculture or industrial IoT node, you have maybe sensor nodes across a field, across a manufacturing facility, an industrial manufacturing facility. And if you have thousands of these devices or hundreds of these devices, and they're failing at once every month or something funky is happening to them every month, you would require a technician to go out and reset the systems every time you see some type of issue like that. And then you have to localize the sensor node itself to be able to do that. So it's not super practical and not super sustainable. And at that time, that's when you're trying to increase the reliability as much as you can so that whenever you need it, it doesn't happen as often. And the second thing here is robust communication. There's often times where you need devices to work the way they're supposed to work whenever you need them, like in emergency response devices. The device might not be used for maybe years, maybe 1-2 years, but whenever you need it, you want that device to work perfectly. If you're in an emergency, you want that signal to go out into the emergency responders to be able to help you. So that's another case. Continuous crucial processing is also another big thing. We actually have like pacemakers, like in the medical field. You want those pacemakers. Now you have life on the line, and you want those pacemakers to be working at perfect, essentially at 100%. You don't want any type of failures, because any type of failure is going to mean that, you could potentially have fatality. So anything that you can do and that you can bring from your toolbox to make the reliability of that system better, in this type of case is going to be important. And then the last thing here is the valuable stored data. So think about crypto hardware wallets, right? So you have keys that give you access to your cryptocurrencies. And if these keys get corrupted by this phenomenon, that now you have an issue. Now you don't have access to your money, which could potentially be, I think everybody would agree that it would be a really bad scenario. So this is where Maxim comes in. We have, like I mentioned, all our new MCUs come with error correcting code. We have 3 different microcontrollers, which I'll be talking about in the next few slides here. But before that, now that you guys know what ECC is and what it can do to your application, I'm curious if you see ECC really adding value to your device. If it's a yes, then great. And you guys can go ahead and answer right now. You should have it in front of your screen. But if the answer is yes, then awesome. That this is where Maxim comes in and really helps differentiate from the competitors with this new feature in ultra low power MCUs. However, if the answer is no, I think you'll still be very interested in seeing the rest of the slides, because even without ECC, the microcontrollers that we just showed earlier are still very applicable for medical, IoT, and financial applications and consumer applications. So stay tuned there. I'm gonna give you here a few more seconds, and hopefully you guys already answered by now. But so yeah, okay, that's great. So 80% yes, 20% no, which is actually a good response. So let's look at the 3 different MCUs in a little bit more detail, not too much. I don't want to bore you guys either. The MaxStory2665 and 666 family, this is actually a very powerful MCU with a dual core processor. They're both running an ARM Cortex M4Fs, and they're running at 96 megahertz. They have Bluetooth options, so you can either have a BLE enable or BLE disabled. But the cool thing about this part is that you can actually run your Bluetooth stack in this smart DMA under the system block. You have a smart DMA where you can run your Bluetooth stack, leaving the 2 main cores actually available for you guys to run the rest of your applications. There's, especially in a big, whenever you're using this microcontroller as a host MCU, you have a sort of different tasks that you have to perform, and a lot of the times you have to perform them in parallel. So having this 2 free cores is going to be very helpful. The next thing here is going to be the integrated SIMO that we have. This actually allows you to remove an external PMIC, so it's all integrated into the microcontroller. And of course, the error correcting codes. We have 1 megabyte of flash, 560 kilobytes of SRAM, which again, you can enable the error correcting code in both of these memories. Just as an overview, a little bit more like what we're trying to do with this part is to really take 4 or 3 different chips and integrate them to a single chip. It's going to be cheaper. It's going to be a lot less real estate within your PCB. So instead of having 2 different processors, now you have a single MCU that has two different cores. You can run two things. You can save a PMIC, and you can also save the Bluetooth module, maybe like an external Bluetooth module, because everything is integrated into this part. So very, very powerful part. Now, if you guys are not wanting that much power, we also have a variant, which is our MaX32655. This is a new one that we just released not too long ago. It's a single core ARM Cortex M4F. It's running at 100 megahertz, and it also has a co-processor that can run your BLE stack. But in this case, it's actually based on RISC-V. So this is actually a pretty new thing, which is actually allow us to cut the cost of the entire microcontroller. Bluetooth is also going to be available, and it's also going to have a SIMO. So again, if you can still take 2 to 3 chips and convert them and integrate them into a single MCU. And then the ECC, we have 512 kilobytes of flash, 28 kilobytes of SRAM, and again, both of these with error correcting code, which you can enable. And then the third one here, the third MCU that has ECC within our low power micros family of products is the MAX32670. It's running also in an ARM Cortex-M4F at 100 megahertz. And this is a smaller MCU that is aimed more towards sensor hub applications where you want to run a algorithm or some type of program outside the host MCU to free up your host MCU. This is actually a great little part because, again, it has the error correcting codes in the memories. Memories are relatively big with 384 kilobytes of flash and 160 kilobytes of SRAM. So pretty nice little part. We also have a security trust protection unit, what we call, which is a suite of security features. So nice little part for you guys to check out. So if you guys are interested in any of these three parts, I encourage you guys to check out our EV kits. Go ahead and go to the MAXIM website, order some of these EV kits. And I do want to note that our MAX32666, which is the first MCU that we looked at, that one's available in a Feather form factor evaluation platform. And it's actually a tiny board that you can actually plug in different, what they call wing boards, which have sensors and so on. And you can actually bring up a prototype really quickly. So check that one out. I think you'll be able to get up and running pretty quickly. And I think you'll find it pretty useful if you guys want to start playing with ECC or start playing with some of the rest of the features that we just mentioned earlier. So with that, I'm going to go ahead and close the presentation. Thanks everybody for joining, and I'm going to go ahead and pass it on to Brian here.
Thank you, Carlos, for that informative presentation. Before we start Q&A, I want to draw your attention to the Contact Us window on your screen. If you'd like additional info beyond what was covered today, please fill out this form and we will reach out to you. We have lots of good questions that have come in. The first one is, so how do soft errors happen? Carlos?
So I think we talked about...
Excuse me, I guess it's how often.
Yeah, because I think we already answered how they happen, but how often they happen, that's actually a good question. So it sort of depends. We know that the frequency of how often these errors happen is actually based on a lot of an altitude. The higher you are, like if you're in places like Colorado, they actually happen a lot more often than if you're at sea level. Also, the type of process technology that we're dealing with is also going to be a big thing here, because the smaller we go, the more susceptible the transistors are going to be, and the more susceptible for bit flips that could potentially happen. So I would say, I guess if I want to sort of answer it with with a range, I would say that it could be from days to possibly years.
Okay, that's a big range. So the next one we have is, where can I get more information about ECC?
We actually have a video. If you guys are interested even more in how we're implementing ECC into our MCUs, we have a video in the MAXIM integrated website called Fundamentals of Error Correction Codes. And there you guys can, it's a 10-minute video, and you guys can actually look at that, and I think you will find it very helpful if you guys want to get more information in how ECC works and how we do it.
Okay. Yeah, that's underutilized resources or videos online, so that's thanks for mentioning that. Here's another one. Where can I learn more about soft errors?
This presentation, we actually use this, we put it together, looking at different resources from research articles. So in this presentation, if you guys go ahead and download this presentation, at the end of the presentation, we have an appendix with a bunch of different resources to different papers, and you guys can also find even more information there.
All right. Here's another one. I have an application where one of these microcontrollers would be a good fit. How can I set up a meeting to get more information?
Well, here in the slide, actually, we have the email address. If you guys want to set up a meeting, just contact events team at maximintegrated.com, and we would, either me or one of our team members, we will make sure we have a meeting set up with you guys to talk about more your specific application and how Maxim can actually help you guys.
And I think there is something at the end of this webinar. There'll be a chance for you to request a meeting for those who are online as well. So that'll be good. Take advantage of that. Here's another question. What packages are available in these microcontrollers?
Okay, so the first MCU that we looked at, the MAX32665 actually comes in WLP and CTBGA packages, so wafer level package and CTBGA. The MAX32655, which was the cut down version of that one, comes in CTBGA, and also WLP will be coming soon. It's still not available, but will be coming soon in the next few months. If you guys are interested in WLP, let us know, and we could potentially expedite that MCU. And the MAX32670 comes in a TQFN and also WLP in the future. So WLP in all of them, essentially, and we have variants of bigger packages on all the MCUs.
All right, so we got them pretty tiny there, don't we?
Yep.
So here's one for you, since you're a low power expert. So what is the power consumption for these 3 microcontrollers?
All right, so just to give you some rough estimates, the MAX32665, with the same order that we were talking on the packages, that one runs at a 91 microwatts per megahertz. This is running at full speed, 96 megahertz. The MAX32655 actually runs at 71 microwatts per megahertz, and it's also running at full speed, which is at 100 megahertz. And then the MAX32670 actually runs at 40 microwatts per megahertz, and that's when it's running at 12 megahertz. If you go all the way to the 100 megahertz, it's a little more than 40. I think it's around like 50 or 55 microwatts per megahertz.
All right. What is the ballpark pricing of these 3 microcontrollers?
The MAX32665 runs at about $450-ish. This 1K pricing, and the higher you go in volumes, obviously the cheaper price you'll get. The MAX32655 is going to be running at a 1K pricing is at $330 more or less, and again, the more volumes you have, the cheaper it gets. And then the 670, the 1K pricing is at $130. So pretty cheap parts, and considering like everything that they have. So again, I think that the main thing here is to evaluate the parts and to see if it fits your application.
Well, yeah, that's a $1.30. That's a good price.
Yep, very cheap.
All right. Now I actually have a question for you. As I was listening to to your presentation, is ECC something that automatically occurs within the memories, or is that or do you have to like set a setting with the microcontroller to turn that automatically on, or is there a little bit of extra code that needs to be developed?
Yeah, essentially, there's no extra code that you need to develop, but there is. You have the option of enabling it or disabling, especially in SRAM. Some of the 3 micros that we talked about, the flash is actually always on. ECC also always on. But in the SRAM, you have the option of disabling it, enabling it, and this actually through essentially a bit that you have to code during your development. But it's not any hard development that you have to do. It's just a setting that you have to set when developing your code.
So it just sounds like an initialization, 1 line of code kind of thing.
Exactly.
Okay.
Exactly.
Great. Yeah, that's nice. Well, let's see. Let me check our inbox for any extra ones. All right. Well, it looks like that is all the time we have for today. Thank you for joining us, and thank you for your great questions. Thanks to our presenter, Carlos Rodriguez. If your question was not answered during the webinar, we will answer it via email. And after the webcast ends, there will be a pop-up on your screen for an opportunity to request a meeting with our team. Thank you for joining us. Goodbye.
Thank you, everybody.